In this video, we're discussing the extrema of a function f, and I'll tell you what extrema means in just a second. We're going to define some terms. We'll talk about global and absolute maxima. That's plural. The singular of that is a global or absolute maximum. We also have global and absolute minima. The singular of that is minimum. We'll talk about relative maxes, relative maxima, relative minima. We'll define the term critical numbers. Sometimes they're called critical values of a function. And then we'll use the extreme value theorem to find some of these guys for a particular function on a particular interval. So let's discuss what a global or absolute maximum is first. We say that f of c is an absolute maximum of a function on an interval, or a global maximum, same thing, if the following is true. If all of the other y values on the graph are less than or equal to that value for every x in the interval that we're talking about. So let's say the interval that we're talking about is I. So this would be true for every x in the interval I. And the absolute minimum of a function on an interval is this y value. We say that f of c is an absolute minimum if all of the other y values are greater than or equal to that y value. So that's for every other x value in the interval I. So let me give you a picture, show you a little example. Let's say our graph looks like this. Let's make it, well, let's do that. Okay, so this is our function, y equals f of x, and the absolute maximum is the y value right here. That's the largest y value on this graph. Let's say our interval starts at a, x equals a, and it ends at x equals b. The absolute maximum is that y value right there, because that's the largest y value out of all of the y values on the graph. Now, it's not the x value, it's the y value. The maximum is f of that number. So I'm just going to call it y max. That's the absolute maximum of this function. Now, the absolute minimum is the smallest y value on the interval from a to b. So let's look over here. There's the smallest y value. I don't know what that is because there are no tick marks on my graph. But it's just the smallest y value. I'm going to call that y min. And it occurs at some x value. I don't know what it is. I'm just going to call it x naught. So the absolute max occurs at x equals a, and the absolute min occurs over here. So sometimes people call this a global maximum, and they call this a global minimum. Global absolute, that just means exactly the same thing. Now, a relative minimum or a relative maximum has this definition. It looks very similar to what we just did, just a little bit different. We say that f of c is a relative minimum, or let's start with max because we did maxes first over there. We say it's a relative maximum if f of c is larger than, greater than or equal to, all of the other y values but just nearby. So f of c is greater than or equal to all of the f of x for x near c. And if you're saying, what do you mean by near, Miss Townsend? You're absolutely right. It's going to depend on what point we're talking about. So let's see. If I'm looking for a relative maximum, that's a relative maximum because all the other y values nearby are less than that. It turns out all the other y values on our graph are less than that, so the relative maximum and the absolute maximum happen to be the same. But this value, whatever that y value is, that's a relative maximum as well, because that y value is larger than all of the other y values nearby. Now, there comes a point when I make my interval large enough, eventually the y values nearby are larger than that. Like if I go all the way over here, these y values are larger than that y value. Or if I go all the way over here, these y values are larger. But if I stay close to this x value, I'm just going to call it x1, all of the y values nearby, near this y value, are less than that. So this is a relative max. This is also a relative max. I'll say that that happens at x sub 2. That's a relative max. And at x equals b, we've got a relative max as well. So let me actually label those in a different color. So the absolute max is y max. But that's a relative max, that's a relative max, that's a relative max, and that's a relative max, because these are the largest y values in a little neighborhood. And actually mathematicians use that word. I know it seems very informal, but they say it's the neighborhood idea. It just means nearby. This is the largest y value in the neighborhood, this is the largest y value in the neighborhood, so is this, and so is this. So all of these are relative maxima. Each one is a relative maximum. If I've got more than one, I call it a relative max, or we call them relative maxima. Okay, and I bet you can guess what a relative minimum is. We say that f of c is a relative minimum if the following is true. If all of the y values nearby are greater than or equal to that. So these are for x values near x equals c. So we're really looking for sort of hills and valleys. At the top here, or at the top of a hill, we've got relative maxima. A relative minimum will occur, or we have relative minima in the valleys, basically, every time we get to our lowest point on our curve. So it looks like we've got a relative minimum right here, and remember the minimum itself is a y value, it's not an x value, but this one occurs at some x value. I'm going to call it x sub 3. Then I've got a maximum, and then I've got a minimum over here. I'll say that that happens at x sub 4. The y value that goes with that is a relative minimum. So I've got one here and one here. And then there was another one over there. So I guess I should use a different color for this as well. Maybe I'll use a highlighter. I've got a relative minimum, a relative minimum, a relative minimum, and I think that's it. So all three of those are relative, each one is a relative minimum. Together they are relative minima. Or we have another term for this as well. We call these local maxima and local minima. So we say relative or local maximum, and this is a relative or local minimum. And then with the absolute max and the absolute min, sometimes we call those absolute or global maxima or absolute or global minima. It's just another way of saying exactly the same thing. Now, let's say you've got a function, you're trying to find these guys. You want to know, where is the largest y value in the neighborhood? Where's the largest y value overall? Or where's the smallest y value in the neighborhood? Or where's the smallest y value overall for your function? In order to find those points, we're going to look for what are called critical numbers of a function. And let's think about why that might be true once we look at a picture. So let's say I've got a function that looks like this. And maybe I'm just on a closed, well, I put an arrow there. Let's make it not an arrow. So I'll say my interval starts at x equals a, and actually maybe I've got an asymptote. Maybe this graph gets really close to x equals b, but it never actually gets there. It just looks like that. Okay, so this is our function y equals f of x, it's the y-axis. Now if we're trying to find relative maxes, relative mins, global maxes, absolute mins, absolute maxes, all those different terms that mean the same thing. Well, let's think about where they happen. Well, I could have an absolute max or an absolute min at an endpoint. If a function is defined at a, like that might be the largest y value, just like it was over here. That was an absolute max of our function, and it occurred at x equals a. And it looks like from this picture, it's a little bit hard to tell. Maybe we might actually just have an absolute max right here that actually occurs at two different x values, and that's totally fine. You still have that maximum y value, whatever that is. Let's say that that's y equals 10. You could have y equals 10 over here and y equals 10 over there. That'd be fine. But we've got an absolute max. This one occurs at x equals a, and it also occurs at this other x value. I'm just going to call that x sub 0. This one does not have an absolute min, though. So an absolute max. I don't know what the y value is because of the way I've drawn my graph, but we know that it occurs at x equals a and x equals x naught. Now this does not have an absolute min. If you're saying to yourself, but Miss Townsend, look at that arrow, it's going over there. You're right, but that's an arrow. It's going to negative infinity. Now, the function can never actually achieve negative infinity. We never get this completed infinity. It just keeps getting smaller, or larger and larger in magnitude, but more and more negative. It just keeps getting larger in magnitude and more negative. So we don't get an absolute min. If you told me negative 1,000,000 was a min, I'd say, oh, what about negative 1,000,001? Like, we can go further. We can always go further. That's what it means to go to negative infinity. So this one has no absolute min because it goes to negative infinity. Now, let's think about relative maxes and relative mins. The maxes occurred here and here. Here's another one. Whatever that y value is, that's a relative max. It's the largest y value in the neighborhood. I'll call that x1. And I think those are our only maxes. So we've got a relative max at x equals a, at x naught, and at x sub 1. We've got one there, one there, and one there. Now this relative max also happens to be the absolute max. But these guys are maxima too. Well, actually, both of these guys are absolute maxes. This guy's a maximum too. It's just not the maximum of the whole function where it's defined. It's just the maximum on a small interval, like in a little neighborhood. It's the largest y value as long as it stays in its neighborhood over here. That makes sense. I'm personifying these points now. So we've got an absolute max here and here, and we've got 3 relative maxima. Now, the relative mins, let's see, do we have a relative min? Sure. There's a relative min, that y value. And whatever that y value is, it's also a relative min. I'll call that x sub 2, and I'll call that x sub 3. This is the smallest y value in the neighborhood. This is the smallest y value in the neighborhood. I really want to say that there's a min over here, but we never achieve a minimum because it just keeps getting smaller and smaller and smaller. So we've got 2 relative minima, and they occur at x equals x sub 2 and x equals x sub 3. Oops. Okay. Now let's think about what do all of these guys have in common? Well, relative minima and relative maxima are occurring either at an endpoint, okay, or at points like this, these hills and valleys. I've got a relative min down here, and what do we know about functions that look like this? Like, how is this related to anything? Well, if I have a graph, let's say this. If I have a graph and I want to find a relative minimum, it's really easy. I look at the points and I say where are the smaller y values, and where's the smallest y value in some neighborhood. And I'm just looking for hills and valleys, and if I'm looking at the bottom of the curve, that's like a valley, and that y value there is a relative minimum. You might say to yourself, but how would I find that if I didn't have this graph? How would I know that the graph even looks like this? Well, let's think about it. Sorry guys, that was my email. If I didn't have the graph, but I just had the equation of the function, well, these points, I could find these points by thinking about where the derivative is 0. Because the derivative is 0 whenever the tangent line is horizontal, right? The slope is 0. So if the slope is 0, we've got a horizontal tangent line. So I've got a 0 slope there, and a 0 slope there, and a 0 slope there. So it looks like at this relative max and these 2 relative mins, I've got 0 slope. We could also have a relative max or min at the endpoints, okay. And then what about this guy? That was a relative max, and we don't have 0 slope there. We don't have slope at all. We've got positive slope on this side, negative slope on this side, no slope at all because we've got a sharp corner. So it looks like all of the relative maxima and minima, you put those together, you call these extrema. These are extrema, or extreme values of the function. Absolute extrema are absolute maxes and absolute mins. Relative extrema are relative maxes and relative mins. All of these extrema are occurring at the endpoints, and places where the derivative is 0, and places where the derivative is undefined. So we're going to put all those together, and we're going to define a new term. It's called a critical point, or a critical value, or a critical number of a function. This is going to allow us to draw graphs like this and figure out, just given the equation of the function, what it looks like. So the critical numbers of a function, or critical values of a function, or critical points of a function. All of these mean the same thing. Different textbook authors are going to use different terminology, but they all mean the same thing. The critical numbers or critical points or critical values of a function are x values in the domain of the function, such that the following is true. Or x values in the domain of the function that satisfy the following. If f prime of x equals 0, Or f prime of x is undefined, or you could say does not exist because this is both a function and a limit, right? And actually I want to use x naught instead of x. So we're going to think of x as a variable and x naught as a particular value of the variable. So we've got x naught in the domain of the function, and the derivative of the function is 0 there, or the derivative is undefined, then we call that x value a critical number of the function. And I'm going to abbreviate it, critical number of the function f. Okay, so let's think about it. Do all the critical numbers give you extrema? We saw when we were looking at extrema, looking for extrema, we were either at an endpoint or we were at a critical number. But does this necessarily guarantee that the critical number corresponds to a relative min or a relative max? The answer to that question is no, because I've got a horizontal tangent line here, turned out to be a relative min. Got a horizontal tangent line there, turned out to be a relative max. Got a horizontal tangent line there, so we're good. That one, the derivative is undefined, so we're good. But it's a little bit hard to see, and maybe I didn't do a very good job. That was supposed to be a critical number as well. I need to draw my graph a little different. To draw it a little bit differently, draw it differently. There's proper grammar for us. Okay. I can have a horizontal tangent line there too, and that's not a relative anything. It just goes from decreasing to having a 0 slope for a moment, and then decreasing. I don't know, it just reminds me of like pausing for a second. It reminds me of jogging, actually. Like I try, and then I'm like, I gotta relax. And then I try, and then I gotta relax. So you've got, it's decreasing, and then it pauses for a moment, stops decreasing, then it keeps decreasing. So this is a critical number. The x value that goes with it is a critical number. Let's say that that's x sub 4. But x sub 4 does not correspond to one of these relative mins or relative maxes, or absolute mins. So critical numbers may or may not correspond to extrema. So we'll say the extrema occur, let's see this. Extrema occur at critical numbers of the function, or the endpoints of the interval, like we saw with that absolute max over there. I'm going to say, or at the endpoints of the interval of definition. So if we're looking for extrema, finding critical numbers is a great place to start, because critical numbers are potential extrema. Or they correspond to potential extrema. Excuse me. Gosh, I can't talk. Let's say they aren't potential extrema, they correspond to potential extrema. And I had to make that point that they correspond to potential extrema and they're not potential extrema, because critical numbers are x values, the extrema are the y's. Totally different thing. So the critical numbers correspond to potential extrema. We might have extrema at a critical number, but we might not. Every critical number is not necessarily associated with extrema. So I guess it goes one way but not the other. Critical numbers are potential extrema, but critical numbers are potential extrema, but every critical value is not necessarily extrema. I'm not sure if I'm saying that very well, so I'm not even going to write it down. Okay, so keep this in mind. critical numbers are x values in the domain of the function, and they have to be in the domain. Function's undefined there, you've got an asymptote, doesn't matter, it's not a critical number. Where the derivative is 0, where the derivative is undefined, and those critical numbers, those correspond to potential extrema. Those are the x values, those are the locations that give you potential extrema. Okay, so keep that in mind. All right, now let's actually do some problems. Say, well, what does all this mean? Well, sometimes, instead of just looking at a graph and looking for extrema, you're given a function and you want to know what the extreme values are. Or you want to find the relative mins and relative maxes of that function, and you have no idea what it looks like. Well, if you're on a desert island and you really want to graph a function, you want to know what it looks like, you don't have a graphing calculator, you're just sitting there on the sand thinking about calculus 1, you can use this technique to find all the relative extrema of your function. You won't be bored. Like if you're stuck indoors because of some virus, something like that, you can entertain yourself with beautiful absolute extrema of functions like this. So let's do a problem. I'm just being a dork, sorry guys. We're going to find absolute extrema of this function on this interval. And we start with a simple one. We're starting with a polynomial function. And it's actually pretty simple. I think I may have said that wrong. I want to find absolute extrema of this function on this interval. And we are starting with a polynomial, and it's a closed interval. And actually, there's one other thing I need to say before I get into this. I'm so sorry, guys. Okay. So we talked about all of that, and I did not mention the very important theorem that all this set of problems that we're about to look at is based on. This is called the extreme value theorem, and I wrote extrema value theorem. All right, that's okay. No more coffee for me. Let's see. That's not true. I'm going to get more coffee after I make this video. Okay, so we're going to do the extreme value theorem. I'm going to state the extreme value theorem, and here it is. And then after I state it, we'll apply it. The extreme value theorem says that if f is continuous, remember that word, on a closed interval from a to b, so x starts at a and x goes to b, or we could write it this way, the interval from a to b. Then f has an absolute maximum on that interval, and it has an absolute min. And I think we've seen this. I think it makes perfect sense. Oops, don't want an arrow. Let's say our graph looks like this. Let's say that's the interval from a to b. Look, it's on a closed bounded interval. It's continuous on the interval. We've got an absolute max over there, and we've got the absolute min right there. So you can have an absolute max on an endpoint and an absolute min on the interior, or the other way around. You could have extrema on the endpoints or on the interior. You might have both extrema on the endpoints. Maybe it's just a line segment. Absolute max over there at A. Absolute min over there. You might have the absolute max and absolute min on the interior of an interval. Maybe it looks like this. So your min occurs at that x value. The min is that y value. And your max occurs at that x value. It's that y value. And this is the interval from A to B. So our extreme values can occur at the endpoints. You might have extreme values that occur at one endpoint and on the interior, or you might have extreme values on the interior. And notice that if you do have an extreme value on the interior, it corresponds to a point where the derivative is 0, or where the derivative is undefined. Here's another picture. Maybe this is your graph. The absolute max is right there. That's on the interior of the interval where the derivative is undefined. And of course, we've got an absolute min over here in that example. Now, you might not think that that's that extreme. You might say, okay, well, what's the big deal? Doesn't that always happen? Isn't the function always have an absolute max? And doesn't the function always have an absolute min? Why is the fact that it's continuous so important? Why is the closed bounded interval so important? Let me show you some examples where the function doesn't actually have an absolute max or an absolute min. Actually, we've already seen one. This is actually a function that has neither. There's y equals 1 over x squared. This does not have an absolute max. Why? Because the y values just keep getting larger and larger and larger. The y's are going to infinity as x gets close to 0. So, you tell me the max is 1,000,000. I'm going to say no, what about 1,000,001? And you say that, well, 1,000,001, that must be the answer then. I can always add something to it, right? So we never get an absolute max. And you might also think, well, what about the min? Does it have an absolute min? Surely it does. Isn't that getting very close to 0? You're absolutely right, it is getting close to 0. But you're not right about it having an absolute min because it never actually gets to 0. It gets closer and closer and closer to 0, but the y values never get to 0. So this one has neither an absolute max nor an absolute min. Here's another example. Maybe this is our interval from A to B. Maybe your graph looks like this. This one has an absolute max, it's right there. But it doesn't have an absolute min. If you're saying to yourself, but what about that point, Miss Townsend? Well, let's say that approaches y equals 2. The problem is, as x approaches b from the left, the y's never actually get to 2. They just get really close to 2, but they never get there because there's an open circle there. So this has no absolute min, but it does have an absolute max. So yeah, what's the problem with these guys? You might say, does this contradict our theorem? Does this contradict the extreme value theorem? Thought you're always supposed to get extreme values. No, you're not. You get extreme values when your function is continuous on a closed interval. So that interval includes the endpoints. So the function is evaluated there, and you have a y value over there on the endpoints, this y value and that y value. And it's continuous. So it's all in one piece. You don't skip anything. So let's see, which of those pieces is relevant here? Why doesn't the extreme value theorem apply to this? Well, it's not continuous at x equals 0. We've got a problem there. I cannot draw this curve without picking up my pen. I draw this part, I've got to pick up my pen to draw this other part. It's got 2 branches. So it's not continuous, And it's not a closed bounded interval. It goes from negative infinity to infinity, not including 0. So you go from negative infinity to 0, and 0 to infinity. The fact that it's unbounded means it never actually approaches that, or it never actually gets to the y value, y equals 0 either. And then this one is continuous on our interval from a to b, but it doesn't include the endpoints. Since we didn't include that endpoint x equals b, we've got an open circle there. Like this is defined on the interval from the open interval from a to b. So that's the set of all x such that x is between a and b, but x is not equal to a and x is not equal to b on that interval. Since that's true, we don't get an absolute min over here. We happen to get an absolute max, but there are no guarantees. The extreme value theorem is an existence theorem. It doesn't tell you how to find it, but it does give you some guarantees. It says, if the function is continuous, and make sure it is, and you're on a closed bounded interval, you start at a, you end at b. A and b are numbers, and x can achieve those numbers. X is never equal to infinity, so that doesn't count. If that's true, then you're guaranteed to have an absolute max on the interval, and you're guaranteed to have an absolute min on the interval. And just from what we've explored, we haven't proved it, we've just explored it, it's pretty clear. The absolute max or absolute min either happens at one of the endpoints or on the interior. And when it happens on the interior, it happens at a critical point. That's some point where the slope is 0, say it's 0 slope there, 0 slope there, 0 slope there, or where the slope is undefined. And remember, slope is the derivative. Okay, so that's the extreme value theorem. Can't believe I almost went into my examples without telling you the theorem. So let's use the theorem to find the extreme value, or extrema, absolute extrema, excuse me, of f on this interval, and we'll start with a polynomial function. So the first thing I need to do is, if I had a graphing calculator, I could graph it and I could just look at the picture, but I don't want to do that. Our goal is to be able to draw those graphs ourselves. So the first thing I want to do is find the critical values of the function. I want to know, where is the slope 0? Where is the slope undefined on the interval? So we'll start with that. So you compute f prime, and then you're going to set f prime equal to 0 and solve for x. And then once you've done that, you're going to look for x values where f prime is undefined. And that's going to be your list of critical values. Okay, so first we'll compute f prime. It's a polynomial, so this is pretty easy. The derivative of the sum is the sum of the derivative, so we just take the derivative term by term. And remember, if we've got a constant, bring that down and multiply by the derivative of the function there. Derivative of x cubed comes from can be found by bringing the exponent down and multiplying by x to the 1 less power. 3 minus 1 is 2. Okay, so I'll bring my 3 down, do the same thing, use the power rule. Bring my exponent down, multiply by x to the 1 less power. Now simplify. Okay. Now we've computed f prime. We want to set f prime equal to 0 and solve for x. Because we're looking for those points on the graph, remember, that look like this. We're looking for potential mins and maxes. Okay, so we set f prime equal to 0, because that's where we get potential mins and maxes, where the slope is 0. And we solve for x. I've got a polynomial in x. The easiest way to solve a polynomial equation is to factor, if possible. So the negative 6x squared and the 6x have a 6x in common, so I'll factor that out. Actually, let's factor out at negative 6x. And then we ask ourselves, negative 6x times what will give us negative 6x squared? Well, I just need an x. Negative 6x times x gives me negative 6x squared, so we're good there. And then we say to ourselves, negative 6x times what gives us a positive 6x? Well, negative 1 will work, because a negative times a negative is a positive. So this times this equals 0. The only way that happens is if one of the factors is 0. And then we just solve for x. So we get x equals 0. Solve for x. Get x equals 1. Those are critical values. Question is, are there any other critical values? Is f prime ever undefined? Nah. I think we're good. It's a polynomial. Polynomials are always well defined. They work out all the time. Remember the domain of a polynomial is all real numbers. We're not worried about taking the square root of a negative. No logarithms involved, so we don't have to worry about taking the log of a negative number or 0. And there's no division, so we're not worried about any denominator being undefined because we don't want to accidentally divide by 0. So polynomials, we're good to go. This is well defined all the time. These are the only two critical numbers. So we just found them. X equals 0 and x equals 1. Now that we found the critical numbers, we want to find the y values that go with them. Now, to find the y values, you don't want to substitute your critical numbers back into your derivative, because remember, the derivative is telling you the slope. We're trying to find the y values on the original graph, so you need to substitute the critical values into the original function. So you're evaluating f at the critical values, but remember, the reason is you're trying to find the y values on the graph. So when x equals 0, we're going to get this for y. Y is equal to f of 0. So it's negative 2 times 0 cubed plus 3 times 0 squared, which is of course 0. Okay. And when x equals 1, that's our other critical value, y is f of 1. So that's negative 2 times 1 cubed plus 3 times 1 squared, negative 2 plus 3, which is 1. Okay. Now we're looking for extreme values on an interval, and we said we were on a closed bounded interval, negative 1 to 1, or negative 1 to 2, excuse me. Now remember what we said earlier with the extreme value theorem. The absolute max and absolute min can occur on the interior of the interval, but it also may occur at the endpoints. So I need to find the y values at the endpoints too. Because remember, absolute max is the largest y value, and absolute min is the smallest y value. So I've got the y values at the critical values. When x is 0, y is 0. When x is 1, y happens to be 1. That's a coincidence. Now we need to find the y values at the endpoints. So you want to evaluate f at the endpoints of your interval. If the interval is a to b, you're trying to find f of a and f of b. Okay. So we'll have f of negative 1 is 2 times negative 1 cubed plus 3 times negative 1 squared. Negative 1 cubed is negative 1. Negative 1 times negative 2 is positive 2. Negative 1 squared is 1. 1 times 3 is 3. So we get 5. And f of 2 is this. We're just replacing all the x's with 2. That's 3 times 4, which is 12. Negative 16 plus 12 is negative 4. Okay. The smallest one of these y values is your absolute min. the largest y value is your absolute max. So basically, we've created a list of y values. I know that when x is 0, y is 0. When x is 1, y is 1. When x is negative 1, y is 5. And when x is 2, y is negative 4. So the absolute min, the smallest number on this list, is right here. So we have an absolute min of negative 4, and that occurs at x equals 2, and we've got an absolute max of 5, because 5 is larger than 0, 1, negative 4, larger than the other y values. So that's our absolute max of 5, and it occurs at x equals negative 1. I think this is easier to see if you graph it. Now, polynomials are smooth, so there's no sharp corners, and we're on the interval from negative 1 to 2. So at negative 1, it turned out the y value was 5. And at x equals 0, y was 0. And at x equals 1, y turned out to be 1. And when x is 2, y was negative 4. So I think our graph looks like this. So it makes sense that this is our absolute max. And it occurs at x equals negative 1. And it makes sense that this is our absolute min. The minimum y value is negative 4, and it occurs at x equals 2. Now it looks like we've got a relative min here and a relative max there. A relative min of 0 at x equals 0 and a relative max of 1 at x equals 1. So that's the extreme value theorem, guys. That's our first example. I'll make another video with more advanced examples. This is a polynomial. Sometimes with other functions, finding the derivative might be more challenging, or factoring the derivative and solving for the critical values might be more challenging. But the idea will be the same. You're just going to find the critical values. That's the places where you have 0 slope. So we had 0 slope at 0 and 0 slope at 1. And then you find the y values there by substituting your critical values into the original function. Not the derivative. Derivative gives you slope. The original function gives you the y values. And then you also have to find the y values on the endpoints. So our interval was negative 1 to 2, so we found the y values at the ends, and then we just draw it. You don't have to draw it to answer the question, but drawing it helps me. It helps me remember what it is we're doing. We've got the absolute max, the largest y value over here, and the absolute min, it's the smallest y value over there. So that is the extreme value theorem.